Okay, so welcome to this session of the LISA Symposium 14, and we will talk about data analysis. So we will have 3 speakers for the first part of the session. We'll start with Alvin CHUA from Caltech, and he will talk about a needle in an opal field, reimagining Coherent gravitational-wave search. Alvin, can you share your slide?
All right, thanks, Antoine. Okay, let me.
Yes.
Okay. Right. So before I start, yeah, I just want to say, my connection is a bit dodgy, so I think I will, just to be safe, stop my video while I'm talking.
Okay.
And please let me know if the feed, if the sound drops out at any point in time.
Yes, I will let you know.
Yeah, thanks. So, okay, today I'd like to introduce some of my recent work, which is written up in this paper over here. So this idea is developed mainly in the context of memory signal analysis for now, but I will try and argue in this talk that it could also be useful in terms of how we should be thinking about coherent searches for LISA sources in general. Right, so first let's look at the basics. Now, coherent search is important in gravitational wave astronomy because it's needed to find sources with low instantaneous signal-to-noise ratio, and these would not be detectable with like excess power methods. So it essentially uses phase comparisons between the data stream X and some signal template H, and more specifically, it looks at this cross-correlation between X and H, which is weighted by a model for the detector noise. So this very familiar quantity here is a statistic of the data for any given H, but it can also be viewed as a function on the continuous space of templates for some given X. So there are, of course, many such statistics we can define, such as capital X here, which is the standard detection statistic for a single template. Now, the search for gravitational wave signals that are described by this model space then just simply involves finding a strong maxima in such functions and also to establish their statistical significance. So this procedure is known as detection. However, I should point out that mapping X correctly to the source parameters theta for any detected signal is also very important as well. And I will refer to this latter procedure as identification. And it is often overlooked because it can be trivial or unnecessary for many sources, but it still exists at least implicitly. And for certain sources such as Binaries, it's actually even the bulk of the problem. Okay, so coherent search for LISA is quite different from that in ground-based observing due to the distinctive nature of the LISA data stream. So the main difference I'll focus on here is that it's actually far more natural to use stochastic methods rather than a pre-computed grid of templates as done for LVK compact binary coalescences. So this is partly because LISA binaries have more observable cycles in general, and thus they have a larger signal space. And also it's partly because there are stronger correlations between any given signal as well as all the other actual or possible signals in the data. So these two factors actually combine with the high computational costs of certain source models in order to make a grid search, a rather impractical option. So another important point is that we are constrained to use sampling rather than classical optimization algorithms. And this is because the coherent statistics that we use are not globally concave or even log concave on the model space. So in other words, the Monte Carlo sampling of statistic-based probability distributions is actually a more feasible way of exploring the signal space. And so in this way, search actually connects more naturally to inference in LISA signal analysis. And that's because the Bayesian likelihood itself, shown here, is also a coherent statistic. And in fact, on local scales, it has a very simple relation to X, as well as the optimal SNR rho. Okay, there are, however, some practical difficulties associated with coherent search. So in the case of LISA sources, we often find ourselves looking for a very small region or needle of probability in a large search area. So this is especially the case for Binaries and SOPHs. For galactic binaries, the problem statement, I think, is slightly different. So there, we don't just want to find some needle, which is easy because there's so many to find. But the aim is actually to find as many as possible. Now, furthermore, these needles that we're trying to find, they are not on a hill, by which I mean there's no global gradient in the search function that leads to it. And this is the main reason why both sampling and optimization do not work very efficiently. So this gradient in the search function is either 0 in the case of X, the detection statistic, or for the log likelihood, it's driven by the optimal SNR of the unnormalized templates across the signal space. And that actually is even worse because it could actually take us away from the actual signal. So it gets worse because the search area is often the proverbial haystack or even a field of haystacks. And by this, I mean that there are many other regions in the model space that can look like signals as well to different extents. So these typically arise from two sources. One, there are the random correlations between detector noise and templates. So these actually cause low amplitude variations, but they do cause them everywhere in the model space. Second, correlations between the actual signal and other templates can also cause larger deterministic variations in the search surface as well. So this second point is particularly severe for MREs, and it has been characterized qualitatively in a recent paper that I wrote with Kurt Cutler. So that's referenced here. Okay, so all of these difficulties are essentially epitomized by MREs in particular, and that makes actually the identification of MRE signals quite intractable. So the first factor for this is that the scale of the region we need to find for MREs is at least 10 to the 20 times smaller than that of the full space. And second, the secondary maxima in the search surface can both be very prevalent as well as very pronounced. So in the study with Kurt, we found that a typical MRE signal can give rise to hundreds to even thousands of such maxima. So that's sort of depicted in this figure over here. And furthermore, the overlaps of all these non-local templates with the signal can be as high as 0.8. So essentially, they look like different sources with 80% of the actual source SNR. Now, one of the key insights from our study is that strong secondaries in the search surface, they have a very generic cause. So they require only the dominant frequency harmonic mode in both the signal and the template being nearly phase aligned for a good fraction of the observation duration. So I'll be coming back to this point later in this talk, so please remember it. Okay, so far we've only been looking at standard coherent statistics such as X or the likelihood L. Now, it's long been recognized that these can be difficult to search. So there are already various modified search functions in the literature that are actually geometrically different from either X or L. So these generally fall into two classes. The first of which is the principle of partial maximization or marginalization over some degrees of freedom in the signal. So examples of these sorts of approaches include semi-coherent statistics, where the data and the templates are partitioned into shorter time segments, and then the data template cross-correlation is maximized over time or phase shifts for each segment before they are being resummed over all segments. So that's this example on the left here. Now, F statistics are another way to do this, where some basis for the signal space is considered, and then the data template residual here is analyzed, analytically minimized over the coefficients. So that's this example on the right. So all of these types of functions, they are essentially less informative comparisons between data and template. And so their general effect is to de-emphasize variations in the search function by broadening and coalescing peaks in the surface. However, something that's maybe a little unappreciated is that these partially maximized functions, they still retain variations due to both signal and noise correlations. And so the picture we have here is really still that of a haystack, but just with a bigger needle. Okay, there's another main way of modifying these search functions known as annealing, and this is often done as part of algorithms such as parallel tempering MCMC. So this de-emphasizes variations in the simplest way possible by just a rescaling of the function. So for example, the log likelihood here can be heated up by a temperature of T, So such approaches, they essentially smooth out the search function, in particular variations due to noise. But one thing to note is that they still actually retain strong secondaries relative to the primary peak. And so the picture here might be that of the same needle, but in a sparser haystack. So all of these approaches are perfectly sensible and they're quite well developed, but to me, none of them really seems to cut right to the chase. So here's a slightly heretical proposal. So I'm suggesting to let's stop looking for needles in haystacks altogether. I think it's suboptimal. So the most optimal thing would be if we were able to put the needle on a hill, as I mentioned earlier. But if you think about it, there's really no way to do that. So I argue that the next best thing is to put it in an open field. And more precisely, I want to explore coherent search functions where all unwanted variations in the surface are exponentially suppressed. And at the same time, it's important that such a function preserves all wanted variations, which is to say we must still have strong peaks at the parameters of any actual signal. And while we're doing this, we might as well try to do even better by requiring that the function be analytically tractable, to have no tuning parameters, and to be fully informed by the template model. So if we can achieve this, then such a function essentially provides us with a one-stop solution to gravitational wave signal analysis, at least at the conceptual level. Okay, so to construct such a function, we basically need comparisons between data and template that are more discriminative than the standard cross-correlation, which is really just a single number. So a natural way to do this is to perform some sort of decomposition of the template into modes, which can then be compared against the data to provide extra information. So we can impose certain conditions on this decomposition here. And in words, really, the template model just has to be well represented by an orthogonal mode basis, but where the modes actually are required to have substantial power. That's this crucial first inequality. Now, for MREs, such a decomposition is available from the start because modeling and analysis approaches rely strongly on the decomposition into harmonics of the three fundamental frequencies in the signal. So here's a spectrogram for a typical MRE signal, and the tracks in red highlight the 4 harmonic modes that contribute nearly all of the power for this particular signal. So for SOBHs with generic eccentricity and precession, it's pretty much the same story, except that working with the frequency harmonics is a less common practice, and so these may need to be extracted from PN models. Now, for galactic binaries, there's no such complexity in frequency, but we might still construct a mode decomposition that satisfies the above conditions, for example, by partitioning the signal in the time domain. So it might be possible to use this new approach to help with the problem of source separation, but actually I haven't looked at this closely yet. And finally, for massive black holes, which generally have a lower eccentricity and precession than MREs and SOBHs, we could go the other way by doing a partition in the frequency domain. So, of course, for such signals, we already have decompositions into angular modes. But these higher modes, actually, they don't contain enough power to provide useful information for this approach. Okay, so the function I'm proposing has this general form. It combines information from 2 standard statistics, capital X, which we've already seen. That's the detection SNR, and plus a chi-squared like statistic here, which is defined using the detection SNR of the individual modes. So as a concrete example, this function can then be calibrated for MREs through the definition of this the function beta, which is not a statistic of the data. So beta is built from information about the signal space at each parameter point. So more specifically, it encodes the optimal SNR row of each template, along with the fractional SNR of its dominant frequency harmonic, which I denote by alpha. So recall from earlier that the strongest secondaries for MRE signals are due to aligned dominant modes between the signal and the template. So the upshot of this calibration is that it reduces the typical height of such a secondary to the original level of noise variations, which is 1. And in the process, it also effectively eliminates actual noise variations by suppressing them to 0. So for other source types, it should also be possible to define beta in such a way as to be useful. But of course, we will need to come up with a concrete problem statement first. So for example, the aim might be to improve source separation for galactic binaries or to speed up searches for massive black holes. So that's work that's yet to be done. So here's a demonstration of the function for an example Emery signal space that's parameterized by 6 intrinsic source parameters. So there are a lot of curves in this plot, but let's focus first on the solid rate curve, which is the function f for an observation duration of 6 months. And this is f evaluated along a straight line that's drawn between the signal parameters and a strong secondary in the 6D space. So the red curve, you can see, has virtually no variations in it other than the main peak. And it's only marginally narrower at its baseline than the standard statistic x, which is the black curve. And this remains true even if you, no matter how you anneal x, and if you do so significantly, you get the gray dash curves. Now, the purple and blue curves here, they correspond to semi-coherent statistics with 6 and 12 time segments respectively. And you can see that they do broaden the primary peak as advertised, but they don't actually do anything about the small scale noise variations. So you might say that the narrow peak in the red curve is going to be harder to find than that in the purple or the blue curve when you're doing a full dimensional search. So if that's true, one can still use less informative comparisons in combination with exponential suppression in order to broaden the peak as well. So for example, if you just do a simple truncation of the observation duration to 3 months, that gives the dashed red curve in this plot, which clearly has a broader peak. But to be honest, I don't even think the narrow red peak will be harder to find because I'm convinced that the broader peak in these semi-coherent functions is actually not going to be enough to offset the greater difficulty with which the chain actually traverses the rest of the space. And of course, the ease of traversability for any search function is directly related to how smooth it is. So this may sound a bit obvious in hindsight, but it's also straightforward to show using a metropolis Hastings chain that I direct along the line from the secondary to the signal. So this figure here essentially shows 1,000 realizations of such a chain for 4 of the functions in the previous plot. The vertical axis here is the location of the walker. And the solid lines, basically, they indicate the median location of these 1,000 chains over time, which is the horizontal axis. So the chains that are traversing the function f are indicated in red, and they are the fastest on average because f is simply the smoothest in the probability tails. Okay, so in summary, in this talk, I have claimed that all of the existing coherent statistics that are used in gravitational research, they are actually suboptimal in terms of efficiency. And this is solely due to uncontrolled variations in the search surface. So to address this, I propose a new class of coherent statistic that exponentially suppresses such variations to a constant baseline over the model space, while it also retains strong peaks at the location of actual signals. I also then demonstrate that these type of function can be calibrated for Emery's in a natural and well-defined way. Okay, that's all. Thank you.
Thank you, Alvin. Thank you very much for the talk. Any question for Alvin? You can raise your hand or ask question in the chat. Wait, I don't see any question. I have a question. How do you calibrate beta, this particular function that you have in because it seems important. It seems to be the key point of your method, this calibration of the.
That is correct. It is the key point when applying this.
And how did you come with this function that?
Yeah. So yeah, it is actually the important thing. You're absolutely right. So for Emery's, basically, it is informed by the fact that the strongest secondaries, as I mentioned, they are caused by essentially the template and the signal having dominant modes that line up pretty much for the whole duration of the signal. So from that knowledge, you can actually say that you can, for any given template in the space, you can calculate roughly what's going to be the overlap with another template that matches just the dominant mode. So using that information, you can then essentially say, I want to reduce the height of such a secondary to 1. And that's done throughout the space. So that's essentially how the calibration is done for Emrys. Yeah.
Okay. Tyson, you have a question?
Yeah, so preface that I warned I had to be multitasking this morning, so I might have missed this. But your replacement of the standard statistic with this new function, is that purely for the sake of sampling efficiency, or does this, effectively like replace the likelihood as part of the thing that you are sampling over?
Right. So no, it's not a replacement for the likelihood, because the likelihood is pretty well defined. So what it is I think what you said at the start, it is mainly just driven by the need for sampling efficiency. And in particular for Emrys, which is the first thing this is applied to, sampling efficiency takes a very huge hit because of the presence of strong secondaries. And
right. So at the end of the day, the samples that you get are the equivalent to samples that you would get from sampling the old-fashioned way, just much more quickly. So you don't have to worry about, implicitly reweighting the prior, basically, because you've changed the statistic.
Yeah, that's sort of correct. Actually, there is a sort of a close relation between the function and also the log likelihood as well. So I think in this paper, I actually tried to argue that if you just sample from the function, you do end up with a final set of samples from that distribution. And I argue that it's generally always slightly broader than the bulk of the posterior itself. And if that's the case, then well, it's broader, but it's not too much broader as well. So it's pretty well localized. So if that's the case, then it could work pretty well for prior localization, or even if you want to use the samples directly, you could just assign importance weights to them. So that's the idea. But they're not exactly posterior samples, if that's what you're saying.
Yep.
Thank you. If there are no other questions, thank you, Alvin, again. And
thank you.
Thank you for this very nice talk, an interesting method. We need to do that in practice. And now we will switch to Alexandre TOUBIANA from AI. We'll talk about the detectability and parameter estimation for Gravitational-wave catalog 3 event with laser.
Yes. Hi, Alvin.
So, Alexandre,
yeah.
Okay,
Can you see
we can see your slide. We see the bar with 30 slides. That's a bit scary, but
No, don't worry. It's a lot of backup slides.
Okay. Okay, you can start.
And if I change slides, you'll see, right? Okay. So hi everyone. I'm very happy to be here today to talk about this work that I have carried with Stas Babak, Siva Massa, and Sergei Osokin on the detectability and parameter estimation of events in GWTC3 with LISA. So the interest for the detection of stellar mass black hole binaries with LISA has grown a lot after the detection of the first gravitational-wave event, because at that time it was suggested that this event could have been detected by LISA, leading to multi-band observations with LISA and ground-based detectors. So since then, there have been many studies on these multi-band events, and it has been shown that they could allow to measure low-frequency modifications to the gravitational signal, which could be due to modified gravity or astrophysical effects. Another interest of detecting the systems with LISA is that by the time they're in the LISA band, they could still have large eccentricity, and this eccentricity information could be used to distinguish between different formation scenarios. However, the population that we expect of the system that we expect to detect with LISA, it's largely unknown. So we could use on one side astrophysical simulations to predict the population of events. However, well, so those rely on a set of assumptions, and also they tend to give the results tend to disagree. There is no consensus yet on what to expect. We could also use the results from the LIGO-Virgo collaboration population in France. So use some of the models they have fitted against data for the population of star mass black hole binaries, but this is again somehow model dependent. So here instead, we use a more data-driven approach. So the idea is to use the events that directly use the events that LIGO and Virgo have detected so far, so that have been released in this gravitational wave catalog, and to see which of these events could have been detected by LISA and how much would the parameter estimation for these events improve by using LISA. Okay, so what LIGO and Virgo give us is, so for each event, we have samples for the parameters of the system. So for each event, we use the samples for the masses, the spins, taking the projection on the orbital angular momentum axis, the inclination, and the distance. And moreover, we assume that the binary, so here we will just focus on the circular binary case. However, we randomize for each of these samples the sky location, the polarization, and phase. Now, so the last parameter to fix is the time to coalescence. So in this study 2 years ago, we had shown that actually this is a very important parameter so depending on at which stage you observe stellar mass black hole binaries with LISA, the result for the parameter estimation in particular can vary a lot. The best being to observe the system closer to merger when it starts chirping. So for this reason, we consider here three different possibilities, so three combinations of time to coalescence and observation time. And finally, so after having defined mock LISA systems with this procedure, we compute the signal to noise ratio using the science requirement PSD, and also the current best estimate, which in the frequency range where the sources evolve is lower, it's better by a factor square root of 1.5 than the CIRGV1. Then we consider two different thresholds for the sources. So one for direct observation with LISA. So the idea is that we would observe them before ground-based detectors. And for this, we take a SNR threshold of 8. And we consider another threshold for archival searches. So the idea being that after ground-based detectors would have detected the source or have a better idea of the parameters, we can decrease the size of the parameter space to look for the source, and we can use a lower SNR threshold, which here we take to be 5. I will not enter into the details right now. You can ask me later, but we do give in the paper somewhat justification for these thresholds. Then, for each of the events in the catalog, we compute the probability of direct detection and of archival detection by computing the fraction of samples that have SNR above 8 and 5. Okay, so to show now the results. So if we use the current best estimate PSD, so here I'm showing the distribution of signal to noise ratios for all the systems in GWTC3, and in color I'm highlighting the systems that for each of the time to coalescence observation time combination have a probability of being detected for a archival search above 10%. And you can see that, as expected, if you observe the systems closer to merger and for longer, the SNR increases, and so does the detection probability. So being now a bit more quantitative, I'm showing this detection probability for a few systems. So first, if we look at the first gravitational wave event, you can see that it's very likely I mean, almost essentially guaranteed that we would have detected it through archival searches, but not so certain that we'd be able to detect it directly with LISA, in particular if we were to observe it far from merger. Now, this other system here is the only one that has a higher than 10% probability of being directly detected, and this only in this most optimistic scenario. And then you can ask the question of probability of detecting at least one system in the whole catalog released by LIGO Virgo. And so you can see that the values that I'm showing here are actually very similar to the one in the first column. This is because this event is really driving these values. So instead, we can ask the question of detecting at least one system other than GW19 or 914. And an important remark that actually in each of the columns, I am assuming here that all the events are detected exactly at the same time before coalescence, that they have the same time before the coalescence and observed for the same period, which is certainly won't be the case. So actually you can see the leftmost column as the pessimistic case and the rightmost as an optimistic case, and take them as lower and higher values. So you can see that it is reasonably likely that we would detect at least one other system than the first gravitational event through archival searches, but it's much less guaranteed that we detect any other system directly with LISA, even in the most optimistic configurations. Okay, so now addressing the question of parameter estimation for some of these systems, we focus in on the most optimistic case, and we consider one system that would be directly detectable with LISA, and another one that would be detectable only through archival searches. Moreover, so we mimic a multi-band detection by using a Gaussian prior in the Bayesian analysis, and the covariance for this Gaussian prior is computed using the samples released by LIGO Virgo for masses, spins, distance, and inclination. And in addition to that, we fix the coalescence time of the binary, because this is a parameter that is usually very well measured by ground-based detectors. We also mimic a LISA with Einstein telescope scenario by just rescaling this covariance matrix by the relative gain in signal-to-noise ratio from LIGO Virgo to Einstein telescope. And an important point is that this is a very conservative assumption, because we are neglecting the fact that ET would actually observe the system for much longer due to its improved sensitivity at lower frequencies. And this has would have in particular big impact on the measurement of chirp mass. But this still should give us an idea on what LISA could help improving in the parameter estimation. So if we first look at this one system, which is directly detectable with LISA, you can see that actually LISA can, so here I'm showing, sorry, the 90% confidence interval in the chirp mass symmetric mass ratio plan. So you can see that LISA could perform actually much better than current LIGO and Virgo, and that it can measure the chirp mass also better than with this rescaled Einstein telescope that we're considering. However, it performs much worse for the mass ratio. And so combining these, when you look at the estimation of the individual masses, adding LISA, in fact, gives only little improvement, as you can see on the right panel, comparing the orange and the purple curves. We have a very similar picture here for the spin. So LISA can measure quite accurately one spin combination, so the effective spin, but not so well the corresponding anti-symmetric combination. And when you translate into individual spins, adding LISA, in fact, has not big impact on the measurement of individual spins compared to using ET alone. Now, if we focus on this other system, which is detectable only for archival search, so it has LISA SNR around 5. So there is no, here we don't have a LISA only case, but we can see that adding LISA to each actually, so again, improves a lot the measurement of the chirp mass and also a bit for the mass ratio. And in this particular case, once you combine this, and you see for the individual masses that LISA can help improve a bit the measurement of the masses. And finally, so for the spins, it's again very similar picture. It can help improve a bit the measurement of the effective spin, not so much of the other spin combination. And so it has almost no impact when you look at individual spins. But it's important to stress again that this is a very low SNR system in LISA, so around 5. And we see here, at least for the masses, that it still has some impact on the measurement of the parameters. So just to mention a few other parameters, so the sky localization, and just to remind you that here I'm using LISA only, I'm not using any information coming from ground-based detectors. We get that for the system that is directly detectable, it's measured within 1 square degree and within 2 square degree for the other system due to its much lower SNR. Finally, for the distance, so the distance measurement is essentially driven by the prior that this ET prior that we are using. So when we use it, we can measure the distance within 5%, and when we don't use that prior, so we use the LIGO-Vigo prior or no prior at all, we can see that the measurement is much worse. Okay, so as a conclusion, so here I've shown that the detection of GWNC 914 with LISA would have been almost guaranteed, at least through archival searches. However, if we want to look at the rest of GWTC3, it's rather unlikely that we would have detected any other system directly with LISA. And perhaps, so we could have, so it's more likely, although not certain, that we would have had some archival detection. Finally, so also I have shown here that even for rather low SNR systems, we find that LISA would improve the measurement of chirp mass and effective spin, but usually when you translate that into individual masses and spins, LISA has smaller effects. And so just to say now, for I think some important improvements to our work would be to proper multiband, not only using these priors as we did here, and also very important to include eccentricity. And so there have been some important steps in this direction very recently. So yeah, I hope I have convinced you that there is still some interest to look at stellar mass black holes with LISA. And yeah, please don't hesitate to ask questions.
Thank you very much, Alexandre. Question, Tyson?
Yeah, I have a lot of questions. So
okay,
the one I'll ask first is, so by reducing the detection threshold, what you're effectively saying is you have fewer degrees of freedom in the search. Which parameters are you not searching over?
So, okay, sorry, maybe this I was not clear enough. We are not performing a search here at all. So, okay, we are not really performing a search. We start always from the true signal. And when I reduce the SNR threshold, I mean, what I'm considering is more the fact that the whole part that I can decrease the size of the parameter space rather than decreasing the dimensionality of the parameter space. But one interesting thing that we found is, so here I'm showing, so the change that for one particular system, which had SNR in LISA, as you can see, of 4.5. So we started our chain from the true point, but you can see that at some point, the chain loses the signal and then finds it again, and then loses it again. So you can see here in the chirp mass, or also in we look at the log likelihood values, you can see that when you're exploring these much broader regions, which correspond to the prior that we're using, it corresponds to much lower likelihood values. So although originally we're not performing really a search because we're starting from the true point, in the end, what we find is that if the system has a Lisa SNR below 5, even in this case, you could lose the signal.
Okay, so then I guess that dovetails to my follow-up question. So what are you doing about the time to coalescence here? And the reason I ask is because, like you said, eccentricity is really the strongest lever arm. And in the LIGO Virgo Kagra band, there's not all that much eccentricity to measure. I don't have much intuition here, but I imagine small fluctuations within the, effectively zero measured eccentricity at merger make for large fluctuations in when the signal leaves the Lisa band, and certainly completely washes out things like the phase of the signal while it's in the Lisa band. So how constrained are you on just the effective time of coalescence when you're doing the analysis in the Lisa band, and how much uncertainty do you think there is in that parameter once you consider very small residual eccentricity?
So as I said, here we are taking only circular binaries. So here we don't have eccentricity, and unfortunately I never so far have not considered eccentricity when doing parameter estimation for these sources. So what I can say is that for the time to coalescence, usually if I don't put any additional prior with Lisa, it's measured within 30 seconds, 1 minute. So I don't know if, yeah, I think I cannot say much more than that, unfortunately, because as I say, I have not used really eccentric waveforms. But I think this is indeed very important steps now to be done. And as I highlighted at the end, I think we're starting to be able to do it now.
Yeah, so I mean, you mentioned it as future work. I'm very excited to see that future work.
Thank you.
Yeah, me too. I had a question about when do you think that already are we for considering eccentricity in this kind of study?
So there has been a first full parameter estimation with eccentricity, so by Antoine Cliental.
Yes.
So I think, I don't know if Antoine is here, but I think one of the major issues right now is the computation is very slow because of the waveform, but they managed to do a full parameter estimation. So I think now we should be able to start doing this.
Okay. Thank you. Any other questions for Alexandre? Yes, Chengju, please.
Okay, can you hear me?
Yes.
Okay, I have a question. Have you considered the noise when you try to search the signal? Will that, or if so, will that affect your parameter estimation result?
Right, good question. So indeed, I did not mention that here we are working in the zero noise approximation. And yes, so definitely also, I mean, if you just what this plot is telling us is that once we add noise for these lower sources SNR, so you could expect that this would drive you away from the real signal.
Yes.
So, and then if you increase the parameter, so yeah, the main effect of noise should just be to move you within the 90% confidence interval. So that, yeah, I think so it's a very good question, in particular for these lower SNR sources. So no, we did not consider it, but this is also something actually that we were discussing recently with Sylvain that we should certainly account for in this low SNR source. For as you go higher in SNR, I think this is less of a problem, but yeah.
Okay, yes, because most of the stellar mass binary black hole signal, their SNR will quite low in the space-based band, right? So
yeah.
sometimes consider the noise, the SNR will be too low, and it's take quite a long time to let the MCMC or their teams to conserve to the true signal. So I also think it's a really good problem to consider.
Yeah, I agree. So I think that's one of the things also we want to look next is now doing the full PE adding noise. Because indeed, I mean, this is, so what you're saying is in fact exactly what these plots are showing is that most of the systems will have really rather low SNR in these.
Yes.
At least based on what LIGO or Virgo have seen so far.
Okay.
Okay.
Thank you.
Thank you.
Thank
Any
you.
more questions for Alexandre? If not, thank you, Alexandre, again for this very nice talk.
Thank you.
And now we will listen to Connor Weaving from University of Portsmouth about the search of massive black hole binary with PyCBC. Connor, are you ready? And can you share your slide?
Hi, yeah, I'm just setting up now. How's that? Can you see everything and hear me okay?
It works.
Good stuff. Okay. So hello, everyone. My name's Connor Weaving. I'm a second year PhD student at the University of Portsmouth. And my project so far has been on the search for massive black hole binaries using the LDC dataset. And we are currently developing these data analysis tools to be implemented within PyCBC, so an open source bit of software which everybody can use. Yeah, just a note on that, obviously we are developing all of these tools within PyCBC, but we are also looking to expand into other open source bits of software as well, such as Bilby. But yeah, currently it should only be available through PyCBC, but yeah, hopefully we'll move on to Bilby as soon as everything's settled with PyCBC. So let's jump straight into it. Yeah, as mentioned, we are building this data analysis pipeline to detect massive black hole binaries, and we are using the LISA Data Challenges dataset in order to help us do that. And we're using these Sangria datasets. We're using the massive black hole binary dataset. And this dataset in particular contains, well, this is the blind dataset that we're using to actually build the pipeline, and we've got 15 signals here which are hidden in mock LISA data. Yeah, so this is what we've been using to train and build all of our tools. So what constitutes a pipeline? What is the purpose of what different sections are there to these pipelines? And they're normally split into two different things. So you've got the search part of a pipeline, which is basically where are the signals within the data. And we use our basic techniques such as match filtering, and we are looking into template bank searches in this particular case, which I'll tell you a bit more about at the end of the presentation. And then you've got the second part, which is the inference, i.e. what parameters, values are there of the gravitational wave signal that we've found. So yeah, so the first part, we'll start with the search. Apologies, for some reason the slide seems to be a bit, seems to have changed slightly. I'm not sure why, but anyway, the quality on the left is a bit rubbish, but anyway. So yeah, we've got our standard match filter. So the animation on the left demonstrates this. The blue line is just gravitational wave strain data. The yellow line is a gravitational wave template. And the red line is the SNR time series. So using this equation on the left-hand side here, which this is the SNR, you should be able to find a peak within the SNR when given a template and some data, and that will tell you roughly where this peak is within the data that you're given. So this is all implemented and done within PyCBC, which is great. So this is just one example of just one match filter search, and this is just using one template, I should say, over the entire year's worth of data that the LDC have for the Sangria dataset. So as you can see, there are multiple peaks across the entire year. So I think there's 14 peaks here which you can distinguish. We know there's 15 in here. So yeah, it's pretty good going just with one template that you can pick out all of these different signals all at once. Previously, we were using code which we wouldn't be able to implement into PyCBC because it wasn't open source. However, a big shout out to Michael Katz, who released his fast waveform, well, fast TDI generation code, BBHX, and that's what we are using as our waveform generator within PyCBC for all of this stuff, right? So yeah, the template bank generation is done with this waveform generator, and the inference as well when we're generating new templates. It's all using his waveform generator. Again, apologies, for some reason my slides are going a bit strange here. There is supposed to be more on this slide, but anyway, yeah, moving on to the second part of the pipeline, you then have the inference, right? So we've already seen that we can find all of the signals within the data, but when we find them, we need to then infer the properties of that signal, and that's using Bayes' theorem here, right? There should be a picture here, but anyway, we'll just ignore that. Yeah, I'll skip on to the next slide actually, because there's a nice corner plot here. So originally we started using the marginalized phase model, and only one TDI stream for simplicity, and you know, we'll build complexity as we go. So here's one of the very first plots that we were able to plot using PyCBC and the waveform generator. So it's very simple, and as you can see, the masses are recovered quite well, but the time of coalescence is off and the distance is off. But after fixing bugs and adding more complexity, we managed to solve the time of coalescence problem. As you can see, I've added spins into this posterior graph as well. But you know, there's still some slight problems with this, mainly due to the amount of time that the marginalized phase model takes to infer these properties. So we had to find a different solution here, and we looked to relative binning, which is a way of ensuring that you don't have to compute such a complicated integral more than you need to. So for example, if you have a very high likelihood template, you can use that as like a reference template, right? And relative binning uses what's called a heterodyning. So if this is your signal at the top, this can be deconstructed into a higher frequency component and a lower frequency component. And the idea here is that if you have a reference template, a very high likelihood, so you're very close to the peak, very close to the true values, this integral can be computed and stored. And because it's very fastly varying, obviously this is quite a heavy computational cost. But if it only needs to be computed once with the reference parameters, then that's great because you can store that in memory and you don't need to keep redoing this integral all the time. So that means when we're searching near the peak with a new template, this slowly varying template will be the one that we can use. So when we're searching around the peak, we actually only need to compute this very slowly varying template, right? Which makes it a lot faster, which is, yeah, been working very well as well. So this is kind of the pinnacle of where we're at the moment with implementation of the inference. So we have relative binning working. We can use all of the TDI streams produced by Michael's code, by Michael's waveform generator. And this is a search over all parameters apart from some of the sky location parameters, right? And as you can see, it's agreeing quite well and it's looking quite good. Yeah, so with the inference stuff, there are still some slight problems like well-known sky parameter issues. But overall, it's looking sensible. And I think we're coming to a place where we can start implementing this properly into PyCBC and making it a bit more public for people to use. Yeah, so as mentioned, there are still some issues with the sky localization because this dataset is produced using only 2-2 mode waveforms. You get these multimodal sky positions, which you can solve in different ways, but we know that it's going to be a bit of an issue for sky localization, which is fine. Yeah, we're currently still trying to make tweaks to that to make sure that we get sensible results back. But the main thing is going from the search stage to the inference stage, because finding the signals is one thing, but in order to get the reference parameters that you need for relative binning, there's quite a big gap, right? So, you know, you'll generate a template bank, and that template will probably be way off the true value needed, or the reference value needed rather, to then do inference. So there's a couple of ideas that we're searching and investigating there to see how we get from those initial search stage to the inference stage. Yeah, so in summary, the basic tools are almost there. There's still a few little tweaks that we need to do to make sure that it's all smooth. There's still some issues with the sky localization. However, we have done some searches with Sangria, and they seem to be working quite well. So yeah, we're hoping by the end of the year, we will have this all packaged up nicely and available for everybody to start playing around and use. So yeah, thank you for your time. I'm happy to take questions.
Thank you very much, Connor. Question from Tyson.
Yep. So the lore has always been that the parameter space is too large and the targets are too small, and you would need so many templates in the pre-computed bank before doing the search that it quickly becomes unfeasible. And that's sort of what drove people towards stochastic sampling algorithms, you know, decades ago, back in the MLDC days. So are you searching over a more restricted parameter space, or has there been some change of the lore?
No, so yeah, currently we're only really generating, because if I go back to this search, actually, hang on. Yeah, so, you know, given that's just one template, we thought that, you know, we don't need really such a dramatically big template bank to find the pings, well, to find all of the signals within the data, right? So at the moment, we're just testing with a template bank of 100. We're allowing it to randomly generate those templates between quite a large range, quite, well, the full range, right, of what we expect. And we are finding all of the peaks within the data with just just 100 templates. And I suppose the idea that we had was that if we can get all of the time to coalescence with some rough, you know, parameters to start with, then we can begin to sort of optimize and find those peaks. And we've had a couple of ideas about, you know, like particle swarm optimizers and stuff like that to get up to these reference parameters needed for the inference. So yeah, so I know the stochastic route has obviously been used before. We just wanted to try it out and see if it could work. So yeah, does that answer your question?
Yep. And then a follow-up. So when you do this on the Sangria data, are you just powering through the galactic foreground, or are you using data where the galaxy has been pre-subtracted because you are using the training data and know what the right answer is, or what do you do? Yeah,
so we are generating the A and E TDI streams. We're then generating the PSD of the entire year of both of those data, and then giving that along with the match filter. So that's the way that we're doing that. Yeah.
Okay, so it has the galactic foreground in it.
Yes. Yeah.
Okay. So you are ignoring the effect of the galactic foreground and trying to search like that. Okay.
Yes, exactly that. Yeah.
Yan Dong.
Okay, thank you. Can you explain more about the problem of sky localization? I didn't understand it clearly. Thank you.
Yeah, sure. So the problem, as I understand it, is that the injected gravitational wave signals within this data set are of the 2-2 mode only. And there are well-known multimodal effects with just using a 2-2 mode waveform when you're searching for it. So this ceases to be a problem when you're using waveforms that have more than just the 2-2 mode. However, because this is just a 2-2 mode data set, we are searching with just the 2-2 mode, and therefore you have these multimodal sky positions. That you can break some of those degeneracies by searching within the LISA frame, but there are still these multimodal effects. Does that make any sense? And would anybody like to add something on top of that who knows more than me?
Okay, thank you.
I would like to add, the Connor tried to search.
I was expecting that.
Yeah, I saw Stas's hand go up and thought, yeah, okay.
It depends on the duration of the signal. If you don't see much of the spiral, what you see on only merger, and what you measure is the time of when it hits, gravitational wave hits different spacecrafts. And therefore it gives a strong degeneracy in, if you see only merger, and a point which is symmetric with respect to LISA plane, just above and below it. And that is strong degeneracy, which is unfortunately will exist if a massive black hole signal is short. And one of the advices here to go into the LISA frame instead of solar system very center, and then this maxima, this bimodality is quite symmetric, and you can manually explore these two parts.
Christian, do you have a question?
Yeah, so that was a very nice talk, thanks. I was just going to ask about whether you've been able to investigate what kind of sensitivity penalty you have for the 100 template approach that you just described, because presumably if there's a signal in data and you do not use the right template, then you're going to be less sensitive. And obviously for many MBHBs, that's not going to matter too much because the SNRs are so large that you're going to see them anyway. But the fainter ones are higher redshifts, which are quite valuable as well. You might not see these with this method, and indeed you would only really be able to pick these out either with a very fine template bank or with stochastic methods. So I'm wondering if you've been able to assess what kinds of sensitivity penalty you experience with this approach.
Yeah, it's a good question. Currently, no. We're still tweaking and messing around with the template bank stuff. Yeah, we did try to do like a match-based template bank generation with 100 templates, and we did get very similar answers. So at the moment, the idea that we have is just, right, can we just find the peaks? Can we just find something? And then from there, you've got some kind of rough time of coalescence, and then you can do you can pass it on to your optimizer to try and find a peak. But yeah, that's a good question. No, we haven't really thought about that just yet, because we're still, we're kind of just wrapping up the code that does this for you, right? So no, that's probably something that we'll have to look into. Well, sorry, that's something that we'll definitely have to look into. Yes. Yeah, thank you for that.
Okay, yeah, thanks. It's just because I was wondering how if the sensitivity to the parameter space position that your templates are in, if that is not strongly correlated with the true parameters of the signals, but the signal SNRs are very high, then they will have narrow posteriors, and so your the positions in parameter space where your template bank is returning high likelihood might be quite far away from the truth, which is maybe a little bit problematic. There are a lot of the reason I ask this is there are a lot of methods for identifying very bright transients like this in data, but I was wondering how effective necessarily this was compared to others. But yeah, thanks.
Yeah, thank you. If there are no more questions, thank you again for the talk. And I think we have a break. We have 5 minutes over the time. So Alexandre, what are we doing? We're convening in 10 minutes or in 15 minutes?
I don't mind. I leave it to your discretion, or people can. Well, let's just say that we'll give people the full 15 minutes, so we'll come back at 20 past.
Yes, 20. That's okay. Okay, see you in 15 minutes.